Last 6 weeks or 7 weeks, you guys discussed about shallow foundations. So hope that you must understand what is the foundation systems. So from this week, we are going to discuss about another foundation types, kind of deep foundations. So today I will briefly introduce what is the deep foundation is, and then introduce our course outline and the assessment plan. Then I can give you the formative assessments in terms of pile design. So general introductions. So anyone been to the Dubai? Yeah. Coming this June, I'm going to visit the Dubai to attend the conference. But I'm very excited because we're going to see the Burj Khalifa. It's the tallest building in the world. More than 8 meter height. Sorry, 800. Wow, I can't imagine. So all the way is the concrete and steel materials. And then can you imagine how heavy it is?
Ever wondered how Burj Khalifa, one of the tallest structure in the world, stands tall in the desert, braving huge sandstorms, while your castle just falls when you bounce next to it? Let's talk about foundations, the backbone of sturdy structures hidden under earth. Imagine building your house on a bed of marshmallows. Sounds fun, right? But when it comes to support, marshmallows just won't cut it. But that is the kind of support you can expect from loose soil. So, what to do then? Enter pile foundations. Think of them as the deep-rooted anchors holding your skyscraper down, preventing it from doing the twist and shout. But when you're building a tower on just sand and expect it to stand, the only force you can bank upon is friction. But I'm sure you guys are wondering, how can an 800-meter tall structure stand just on something as simple as friction? Let's do an experiment. Take 2 books, something like yellow pages. Start stacking every page. Now try to pull them apart. Seems easy, right? What happened? That is the power of friction. So, the next time you see a building standing firm amidst the chaos, remember, it's all thanks to the pillars under the ground, the foundations. Stay grounded, folks.
The steel piles were driven deep into the ground, each reaching over 160 feet. On top of them, 12 million gallons of concrete was poured, creating a 12-foot thick base. And this connects the tower's main support columns. From there, the Burj Khalifa is built floor by floor, stretching nearly 3,000 feet into the sky. The steel piles keep it locked into the ground, while the concrete base spreads the building's weight. And this keeps the soft desert sand from collapsing underneath it.
Let's think about Seoul. We have Jamsil Tower. It's the tallest building in Korea and in the world record number 5. This is quite considered as a high-rise buildings. So quite massive. I've been to here, then can't imagine the how massive it is. And then I also prepare some video.
Compare the site condition at the Lotte Tower to other projects in the coastal area, like in China. Actually, the ground condition here is much better.
Lotte World Tower was constructed by excavating down to 38 meters underground and driving 108 piles that are 1 meter in diameter and 30 meter in length onto the bedrock for the further reinforcement of the structure. Then there is a solid mat laid on top, followed by the process with 72 meter in length and width and 6.5 meters in thickness. This massive mat, which is composed of 80,000 tons of high-strength concrete, is much thicker than that of 3.7 meter one by the Burj Khalifa. and contains more than 2.5 times the amount of concrete. In addition, a concrete cutoff wall around the entire building has been inserted into the bedrock to eliminate any possible inflow of groundwater into the structure. The construction site of Lotte World Tower is based on masses of bedrock consisted of banded gneiss, which forms all the structural foundation of the building that also leads to no chance of sinkhole formation. Designed to withstand wind speeds of up to 80 meters per second and seismic intensity of up to 9, making the tower far sturdier than Burj Khalifa.
Finally, I think that the redundancy, that is the ability of the structure to move loads around in the building to take care of unfortunate circumstances that might take place in the building unknown to the designers or to the operators of the building.
What about our Singapore case? Which building is the most famous? Three towers and then one big ship on top. And then I'll be proud to say that a Korean construction company built this, only built. So mentioned to you, so this building should withstand wind speeds and earthquake and live loads. The question is, how are such structures being supported? Yes, of course, foundation systems. But what if the foundation can't support such loads? One of the famous case study is Tower of Pisa. Very famous. Start to lean towards. As you can see, the Tower of Pisa constructed on soft ground, sand, steel, and clay. Keep tilting and tilting, and then reached very dangerous situations. So many of the engineers try to recover it back to original place. So this foundation system secure our building safety and our citizens' safety. So let's go back to our Marina Bay Sands. So do you know how many piles do you have underneath this shallow, the Marina Bay Sands? And how large it is, how deep? Of course, according to our soil profile, soil investigation reports, and then design loads, then we calculate size of the pile and number of piles. So before we talking about the design of the foundations, let's define what are the foundations. I Googled it. What is the foundation engineering first, which is part of geotechnical engineering that utilize the principle of soil mechanics. So yeah, you've already attended geotechnical and soil mechanics. Soil mechanics means soil itself, soil properties, soil behavior, how strong they are. And geotechnical engineering modules, you mostly deal with geotechnical structure, retaining wall and slopes and canal, something like that. The combination of these two, soil mechanics and geotechnical engineering, together with rock mechanics, can determine our foundation design. This is the tallest building. This is our normal condominium and then cluster house. In that case, we can go with shallow foundations. But in terms of our upper structure loads getting increased, we need another geotechnical interface. Transmit our upper structure load into the soils, which is the foundation engineering. So our soils, the superficial layer soils is sometimes very weak. When you step on it, you get down and then get down and sink. Very low, very capacity. And then getting in deeper and deeper, we will have very competent soil layers, which has higher shear strength. So our foundation load is transmit loads directly to the soils. Shallow foundation, same. Deep foundation, same. So we learn about geotechnical engineering modules, and then now you're attending structure modules. When it comes to design of foundation system, we will get loading condition from upper structures, kind of structural engineering, structural engineers. And then our geotech engineers just design according to the loads. You guys only focus on geotechnical things. It is still okay, but we need to interact with structural engineers to get a clear picture of our foundation systems, technically safe foundation systems. So our foundation engineers, as a geotech engineers, we need the broad and deep experience with geotechnical engineering and structural engineering, even construction sequence and construction skills. So why we need foundations? Of course, one of the key role is safely transmit our structural load to the soils. Our load is now 200 kilonewtons, equivalent to 20 tons. The typical load is 1 ton. So we have 20 loads. The wind need support is 20 loads. Then you have this kind of interface of geotechnical structures, which is the foundations. And then considering your cross-sectional areas, the pressure acting on this part is around 400 kilopascal. Probably this 400 kilopascal transmits laterally, vertically to the soils. Just reminds of your civil engineering skill modules, concrete. What is your typical concrete grade? 30 and 40 unit megapascal. 30 megapascal meaning 30,000 kilopascal. Way bigger than our soils and our some kind of pressures acting on our pipes. It means that concrete itself strong enough, very strong. Sometimes we use steel pipe. Steel's the strength much higher than concrete. It means we don't worry about material itself. Let's consider this is the pipe, very strong. The problem is always soils. Soil fail first. That's why the role of our foundation is transmit our building loads. And then our soil should have strong enough bearing capacity. So our foundations typically divided into two, shallow and deep. Okay, let's consider only deep foundations. As you can see here, driven and bore pipe. So later we discuss about these two different types of piles. But off the top of my head, I can say that driven is this hammer, hit, then this pile, insert. Driven, the drill shaft or the bolt pile is we drill a hole first, then we put our steel cage and pour it out concrete, then cast in place. We have two different types of piles, driven piles and bolt piles. Let's take a look at this bottom of the foundation systems. Pile systems and pile left systems. They are similar but a bit different, but considered as the foundations. And then when you take a look at one single pile, looks like that. The blue arrow is our vertical loads, self-weight, live load. These gray things are our single pile and support these vertical loads. When you take a look the pile foundation system, we have skin frictions and end-bearing pressures. Even when you see the bottom of the soil, you have the stiff or rock materials. This pile carry even higher loads. This is complex building systems, high-rise buildings, and then medium buildings, even our shop house here. And then also condition is quite complex, consisting of fill material and marine clay, residual soil, and then some competent soil layers. As the foundation engineers, we need to find out appropriate pile types. For the high-rise buildings, we use caisson. It's a much bigger version of the foundations. And then for the 30-story buildings, we use only large foundation as a shallow foundations. Because the shallow foundation soil layers is a bouldery clay. Is a strong kind of strong soil layers. In between these two buildings, we have residual soil and marine clay. In that case, we can reinforce this area with some bolt pile and driven pile. This is a shallow foundations. I don't want to talk too much on that. One of the deep foundations, the length and diameters ratio is greater than 4, we consider as deep foundations. High pro. These are also deep foundations? Yes, of course. As long as you have your pile length greater than the diameters in terms of 4 times, which is deep foundation. But normally this slender one is the pile, the fat one is the pier or case. Only the different thing is the naming. So before we talk about some design of the pile foundations, let's define our component of piles. Here is the pile head. Yeah. The bottom one is pile toe, even end. And then Along the depths, we have side or skin. Sometimes we have different diameters along the depths, and even we have enlarged base because sometimes we need more bearing capacity. So we can make it bigger and bigger at the end, and then we have more bearing capacity. But this one is typically used in Singapore. I don't see any tapered and then enlarged based foundation systems. Why we choose the foundations? Simple. Our law in your code is so-called actions. Action is very big. Wow. Shallow foundation cannot. In case you go with the foundations. The superficial layer has very low bearing capacity, which means low soil strength. Kind of Singapore marine clay. And then the governments plans to build mega buildings, kind of another second or Marina Bay Sands. In that case, we can consider the foundations. And also, we expect the settlement sensitive buildings, for example, semiconductor buildings and the data centers. In that case, we need strong foundation system. In our deep foundation systems, we have skin friction and bearing resistance. Here, I want to say that let's take a look our shallow foundation first. Okay, just remind. In our shallow foundation systems, we have wedge shapes and then passive and something like that. These are our soils. So this soil, each face resistant. Our loads transfer to laterally and vertically. So our bearing capacity ultimate shallow foundation is simply say C and C, Q and Q, gamma, gamma B and gamma. But here 0.5. What does that mean? Can you explain? Shallow foundation bearing capacity. C and C. C means cohesion. Q and Q meaning embedded depth effects, confining effects. Gamma B and gamma means Withers effects. Combination of these three gives our shallow foundation bearing capacity. What about clay? Yes. The first part is dominance. Second part, C meaning cohesion. So embedded depth is very little. And then with us, still we have wide with us, right? Compared to embedded depth, our shallow foundation with us is more than 2 meters, 3 meters, but depth is less than 1 meter, right? The depth effect is quite significant. But we don't know how significant it is. That's why we times 0.5. Reduce the reduce effects. What about sand? Sand meaning cohesiveness. The first part, less significant. Second part, more significant than seed effects. Because they don't have any cohesion. That's why all materials press down our shallow foundations. This is our ground surface. This is the ambient depth. These soils press down. That's why this bearing capacity increased. The sand materials, this part, second part is most dominant. And then the reduce effect, same. What about just borrow this concept to our deep foundations? Same. C and C, Q and Q, 0.5, half effect, gamma B and gamma. I don't know what's the value of NC and gamma, NQ and gamma. Just read off your graph and then obtain from the tables. Already given value. So C, same. Cohesion with the clay materials is dominant. This one, wow, I prove it is too deep. More than 60 meters, 100 meters. Yes. In the foundations, this one is very significant. This second part contribute our bearing capacity. Wow. What about the B? This B only 1 to 2 meters. Compared to your pie length, this one is very detailed. So we remove these terms. I don't care about how large it is in terms of diameter. We ignore these effects. So in our deep foundation bearing capacity, only consider these two terms, CNC QNQ. So these skin frictions resist our vertical load, and even our pile toe we have end bearing capacity. And here is the ground surface. This soil, right? Confining. Pop questions. Excited. Which road case is the most common in Singapore? Friction and bearing, or only friction, or only end bearing? One third. You just pick one of the things. Friction and bearing combinations is most common in Singapore, or friction only, and bearing only, and bearing only. Okay, later I can answer you. Friction only, and bearing only. Oh, this one, right? Okay, first one. It's okay. Okay, 1, 2. Second one. Only 1, 2. Okay, 2, 2. Last one. 1. Choose. Anything? Oh, 3. Okay. Okay. Even need 2, 2, 3. Okay, later I can answer you. Now, I can briefly talk about the important things. Design. Of course, according to your concept. Design of our pie. Wow, so many texts, but you can read only highlighted one. We should secure bearing capacity, and we do have little settlements. Little 1 mm, 1 meter. I don't know. Eurocode knows. We have to follow Eurocode's criteria. What criteria Eurocode has? Next week. Anyhow, let's continue. So yeah, very wordy. It's okay. It's okay. What you can remember is our pi should have strength, bearing capacity, and serviceability. Settlements. Only 2 things. Singapore standards. Design. Every Singapore geotechnical structures designed by Eurocode. If Eurocode didn't mention about something, Singapore standards supports that local code. So we should follow Singapore National Annex to Eurocode 7 geotechnical design, part 1, general rules. In the general rule, we have 2 things. Foundation must meet 2 principal performance. Strength, serviceability. Strength meaning bearing capacity. What is bearing capacity? Resistance. Pipe itself resistance? No, they are very strong. Also is resistance. And then serviceability, excessive deformation. We have to protect excessive deformations. When you apply your vertical loads, piles moves down throughout the construction sequence. We have to secure certain level of settlement. Your designs meet these 2 criteria, BCA finally approve your design. Definitely approve your design. So, design planning. Okay, sites, construction projects, how many buildings? Now we have east to west, how many stories? Certain the E1 building is higher than this. This is design planning. Okay, let's study. Then we do preliminary design. Oh, how many piles? How long is it? This is the preliminary design. Then we do pile load tests to verify your design. So this foundation engineering module only cover these 2 only. I don't touch on detailed design. Detailed design meaning we count on how many lever, how space. But to be honest, I don't have any experience on detailed design. But there's some framework. When you decide your number of pile, number of your pile lengths and pile diameters, this one is automatically calculated. That's why I do teach this. Very simple and then quite typical work. most important thing is preliminary design and verify these things, this design by pile tests. I will focus on only these two things. These things. This one, when you join your workplace, you're supposed to do these things. But probably your supervisor asks you access questions. Then you type in your file diameter, file length, then everything is done. Very simple. But preliminary design, file tests, we need some engineering judgments. That's why you need to study these two methods from these lectures. So what is the procedure of the preliminary design according to your book 7? First, calculate design actions. How many stories? 1 story, 2 tons. 10 stories, 20 tons. Which is 7 weights plus our human nodes. Wind. Once you confirm your design actions, we calculate resistance from source. After calculating your source resistance, then we can factor them to make it characteristic value. Characteristic value is a Europe code counts. So next week, I'm gonna show you so many equations. Oh, let's go. Wow, a lot. Woohoo! Very complicated. Yes. Clay, sand, skin friction, bearing and bearing. Wow. We calculate soil resistance from the equations. This is our soil resistance, and then factor that resistance. Divided by 1.3, divided by 1.4. That value is characteristic value. We haven't found design resistance. We factor again. Divided by 1.4, 1.35, then finally we get design resistance. Resistance, characteristic value are divided by certain partial factors, and then design resistance, comma, divided by another factors. Then finally, we will get design resistance. Then compare design action and design resistance. So of course, our design resistance should be higher than design actions. Then you can decide number of piles, pile lengths.
We design concrete structures based on design philosophies.
After your preliminary design, okay, pile diameter 1 meter, pile length 33 meters. How many piles? 4 building, probably 16 piles. Okay. I finished. Then you ask subcontractor to do pile load tests. Wow, this is pile. Then apply loads. What loads? Axial load. Axial load. Walking load times 3. Up to 3 times walking load. Then you will get complicated graph. I don't want to talk too much today because one day we deeply discuss about this. So this is the load, this is settlement. When you increase your load, your pi settlement increase. Then two criteria, right? Serviceability. Your pi should exceed certain settlements, shouldn't, and ultimate your bearing capacity. Then we don't worry about structural ultimate limit states because our pi material strong enough. Okay, this is summary. And then after certain lecture topic, I will prepare 1 minute paper, which is simple quiz, not graded, don't worry, not graded. So, before we move to our next slide,